Dilutions. So concentration of solutions, qualitative expressions of concentration. A dilute solution contains a relatively small amount of dissolved solute, while a concentrated solution contains a relatively large amount of solute. Hydrochloric acid is sold as a concentrated 12 molar, or moles per liter, solution. A dilute 0.1 molar solution is commonly found in labs. So this is why we need to know how to take a stock solution and dilute it down into the concentration that we need to actually perform our assays. There's two parts to diluted solutions: the sample to be diluted and the diluent, or the substance that the sample will be diluted into. Solutions are often stored in concentrated forms called stock solutions. So many lab procedures call for less concentrated solutions, so chemists and laboratory scientists must dilute the stock solution to the required concentration. This is done by combining a certain amount of the stock solution with water. To determine how much of the stock solution to use, we use the dilution equation M1V1 equals M2V2. M is the molarity of the initial solution and V is the volume of the initial solution, while M2 is the molarity of the resulting solution and V2 is the volume of the resulting solution. So prepare 5 liters of a 1.5 molar KCl solution from a 12 molar stock solution. So we know what we're starting with is a 12 molar stock solution. But in order to get to the end point that we want, of 5 liters at 1.5 molar KCl, we need to know how much initial volume of the stock solution is needed. So pay close attention to how these problems are worded, because it will give you the information that you need to determine whether it's M1, V1, M2, or V2. So prepare 5 liters of a 1.5 molar KCl solution. This is what we want to end up with. The liters is the volume. So if we're ending up with something, we know it's going to be our 2, so this is our V2. And the molarity, that's our M2. So that's what we are going to end up with. So it's coming from a 12 molar stock solution. So this is what we're starting with. This is our M1. So in our equation, M1 V1 equals M2 V2. We have 12. We don't know our V1. That's what we're calculating. We're going to set, sorry about that, we're going to set that equal to 1.5 times 5. So that's coming directly from the problem up here. Now all we have to do is solve for x. So in order to solve for x, we're going to combine the 1.5 times 5, and then we're going to divide away the 12 from both sides. And our answer is 0.625. Now what unit? Well, we started with a unit of volume as liters, so we're going to keep the unit of volume as liters. Unlike the molarity calculation, we used moles per liter. We don't have to use liters. It's just on both sides, the volume unit has to match. So if we use milliliters over here, we have to have an answer of milliliters over here, or vice versa. If we used liters, we would have to have liters over here. So as long as the units match, our volume units can be whatever. So in this instance, we started with liters, so we're going to end with liters. And this goes through the example of that. How many milliliters of 10 molar hydrochloric acid are needed to make 500 mils of a 0.1 molar hydrochloric acid solution? So pause the video, go ahead and attempt this one, and then we'll work on it together. All right, here we go. How many milliliters? So we're questioning our volume. of a 10 molar hydrochloric acid solution, so this is our M1 because that's what we're starting with, and they're asking how much of this should we start with, are needed to make our V2 and M2. So we're going to be ending up with that solution that's 500 mils at 0.1 molar. How much do we need to start with is the question. So we're going to put this into our equation. M1 V1 equals M2 V2. And they just flip-flop the variables, same concept here. So we're starting with 10 x, because we don't know what that is. We're going to set that equal to 0.1 times 500. So 0.1 times 500. And then we're going to divide away the 10 from both sides to isolate the x. So our answer is 5. Now what's the unit? Well, we started with mils, so our unit's going to be in mils. How many liters of 12 molar hydrochloric acid are needed to make 5.5 liters of 0.25 molar hydrochloric acid? So we're starting again. We don't know our V1. This is our M1, what we're starting with. And we're trying to make a V2 and an M2. So when we put this information into the equation, M1 V1 equals M2 V2. Our M1 is 12. We don't know what V1 is. We're going to set that equal to our M2 of 0.25 and 5.5. So we do 0.25 times 5.5 and then divide away the 12, and we would start with 0.11, and we'll round it to 5. And what unit? Well, we started with liters. We're going to put our units in liters. Your stock EDTA solution is 0.5 molar. You need to add EDTA to your 100 ml buffer at a final concentration of 25 millimolar. What volume of EDTA would you add? Well, the first thing that we have to do is agree upon a unit. So we have this and this that conflict. So we either convert both to millimolar or both to molar. So what I'm going to do is I'm going to convert it to molar. So we're going to have 25 millimolar, 1,000 millimolar is in 1 molar. So we're going to multiply across the top, divide away the bottom. 25 divided by 1,000 gives me 0.025. So now I can plug this information into the equation. M1 V1 equals M2 V2. Your stock EDTA solution, this is what we're starting with. You need to add EDTA to your 100 ml buffer. So this is our final volume at a final concentration of, this is our M2. What volume would you add? So we have 0.5 for our M1, X, because that's what we're trying to figure out how much of that stock we need, equals M2 was calculated to be 0.025 because our units had to match before we put them into this equation. And then we would do times the 100 ml buffer. So 0.025 times 100, And then we would divide away the 0.5 to isolate the x, and we end up with 5. And our unit would be mils. All right, so you have 8.9 molar solution of calcium chloride and want to dilute it so that you have 600 mils of an 8.2 molar solution. So here we can see our M1, and here is our V2 and M2. What is the volume that you would use in this dilution? So M1 V1 equals M2 V2. 8.9x equals 8.2 times 600 mils. So we would do 8.2 times 600 and divide away the 8.9, and we get 552.8 mils. Which makes sense because these are really close. We're just diluting it a little bit. So we're going to use the majority of that stock, and then we will add a little bit of water. So from the previous problem, how much water would you add to the calcium chloride to create this solution? Well, our solution equals the volume of the calcium chloride plus the volume of water. Our solution that we just made is 600 mils, or that we want to make is 600 mils. The volume of calcium chloride that we're going to have to add is 552.8 mils plus x. We don't know what the volume of water is. That's what we're trying to figure out. So you're just going to take the 552.8 from the 600. So 600 minus 552.8. We get 47.2 mils of water. So that's how much water we'd have to add. So now you know exactly how to prepare this solution. You know that you're going to take 552.8 mils out of your stock solution and add that to 47.2 mils of water to a resulting volume of 600 milliliters. So go ahead and pause the video and work through this one. All right, so you have 10 molar solution of calcium chloride and want to dilute it, so you have 500 mils of a 2.5 molar solution. So this is our M1. We don't know our V1. This is our V2 and M2. So when we put this into the equation, M1 V1 equals M2 V2, we have 10x is equal to 2.5 times 500. When we do the math, 2.5 times 500 divided by 10, 125. And that's mils. From the previous problem, how much water would you add to the calcium chloride to create the solution? Well, we have a total solution volume. So the solution is equal to the volume of calcium chloride plus the volume of water. So our 500 mils is equal to the 125 mils plus whatever the water is. So when we do 500 minus 125, we get 375 mils. So to make this solution, we'd get a flask out. We would put 125 mils of the calcium chloride, and then we would fill 375 milliliters of water in there, so we get to a final volume of 500 mils. Dilutions versus ratios. So if you are prompted with problems that say the word dilution, which in the laboratory, that's predominantly what we're dealing with. We don't really deal with ratios too much. But dilution is where the numerator denotes the parts of the sample used, and the denominator is the total parts, so the sample plus the diluent. For ratios, the denominator is only the amount of the diluent. As I mentioned, ratios are not commonly used, so we're not really going to touch too much on those, but I did want to talk about the difference just so that you know. So we're going to be dealing primarily with dilutions. So the top number, this first number that we would see, and it can either be expressed like this or this. This is going to be the sample that's used, while this second number, this and this one, are going to be the sample plus diluent. So this is the equation for determining dilution. What is the dilution factor of a solution that is made of 20 milliliters of sample and 80 mils of diluent? Well, this would be a 20 to 100, or a 2 to 10, or if we want to reduce it to a 1 to 5 dilution. Now, where did I get that from? So the first part of this is the sample. The second part of this is the total solution. So that's the sample plus this diluent. So that's where we broke it down. That's why it's 100 and not 80. And that's our dilution factor. Sometimes you need to work backwards to determine how many parts of a dilution are made up of the sample and how many are made up of the diluent. So for a 1 to 8 dilution, how many parts are the sample? Well, the sample is 1 part. And how many parts are the diluent? Well, this number gives you the sample plus the diluent. So if we rewrite this, this number here is just the sample. This number here is the sample plus the diluent. So if we have 1 for our sample, then we would have 8 minus 1 to give us the diluent. So our sample is 1, our diluent is 7. What are the parts of the sample and parts of diluent in the dilutions below? So I'm going to give you a couple minutes. I'd like you to pause the video and work through these. All right, so no matter how it's written, whether it's with the slash or the decimals here, we're going to go through here. So this would be 1 part of the sample, 34 parts of the diluent. This would be 2 parts of the sample, and this would be 63 parts of the diluent. So you basically just subtract them to get which part of it is the diluent. This is our sample, and 100 minus 45 is 55. So this is how many parts of the sample and how many parts of the diluent.